We're going to be doing two problems. You haven't missed anything yet. The first one is the robotic arm problem. And what we have here is a base here, a stand right there. You can see that. There is a link 1, there is a link 2, and there is a vertical link that is inserted into that hole, and the bottom of this link is supposed to be traversing that path in space. Now, you can view this thing as a welding gun that is trying to do seam welding of two things together. So the bottom of this is where all the action is, and it's supposed to follow that trajectory. That trajectory is the juncture of the two parts that we are trying to weld together, for example. All right. I'm going to ignore all dimensions and therefore do it on the fly. Okay, so let's go ahead here. All right, let's start with open a product file. Immediately, we're going to save it. File, save management, save as, desktop, new folder. Okay, so let me call this thing Lab 52 Robotic Arm. Okay. All right. Let's insert the first part. Insert new part in there. Let me call this thing the base. Right click, properties, properties, base, and base. Okay, let's make it. Double click on the base to go into part design. On a convenient plane, on the XY plane, I will sketch a square or a rectangle. It really doesn't matter. I just want to have an idea what this size is. It's a good idea because I'm not dimensioning. This is 2 inches. Okay, fine. Circle. Another circle. Because I want to do a multipath. You do that stand any way you like. I'm going to do multipath. So, okay, select the sketch. There are 3 curves here. This one is the middle, the middle circle. This one is the periphery here. I'll make it 0.5. Okay, this one is the I can't remember. This one is the middle one. Let's make it 8, 9, and this one is that pin in the middle. So let's make it 10. If it doesn't look good, we're going to fix it. Don't worry. Yeah, that's good. Okay, good, good. All right. So now, when I do this thing, it's not. You can see that the bottom of this vertical link is going along that path. So immediately you remember something: point curve joint. Point curve joint. You need a curve. Now that curve, I can do it as a separate part, or I can make it belong to the base. That's what I'm going to do. All right, so we go up here. Oh, while you're in the base, while we are in the base, I want to draw that thing in space. And the way I'm going to do that is I'll draw a plane here, a slanted plane in the base, and on it draw a circle and use it for that purpose. So slanted plane. The method that we're going to use is we want it to be slanted. So I use this. What is that? Angle and normal. Rotation axis is here. You'll see what these things mean. And the reference is that plane. In other words, it's rotating about that. This plane is rotated about this. Okay? This face is rotated about that. Notice that already it created a plane for me, but that at 0. I'm going to change that angle to something else. Look, it's rotating. See? Yeah, I get there. And then I'm going to draw something on it. Okay, let me actually rotate it a little bit more. Yeah, okay. So on that, I will sketch my path, which for simplicity, I'm going to draw a circle. I'm too lazy. I can do a spline, I can do an ellipse and things like that. Here, let's try this circle. And we're going to watch it. If it's too small, too big, we're going to fix it. There. Okay, I wanted to move it. I want to move it. It's too close to that guy. Exit. I wanted to move it away, so let me see. Let me turn this thing around, see, okay, so that's, I want to move it away, right there. That's good. Okay, I like that. Okay, so we're going to save this. Are there any questions? No questions. Okay. You know what? I want to make this thing a little bit bigger too. Yeah. Looks more impressive. Okay, then we're going to insert link 1. So we go up there. Is there a question?
Oh, yes, Professor. How did you just do that, increasing the size of the circle?
I just grabbed it because I didn't dimension it, I didn't fix it. I just
Okay.
just grabbed it.
Right.
Yeah. Okay, good. So we're going to go there, save everything. All right. Now we're going to insert the next one, which is link 1. Link 1 goes on the top. Insert new part. Link 1. Right click properties. Link 1. Link 1. Okay, let's go make it. Double click on it. On a convenient plane, on that plane, because I'm going to draw these in place so that I have a good idea of what I'm doing. And I'm going to project that circle to get the whole of that link. The whole, H-O-L-E, okay? So let's draw the rest of this. You know, I just realized something before I do the rest of this. The time for this video, because I thought it was starting at 1 o'clock, I think I set it at 2. So I'm going to change that. Yeah, you see this? Because I thought I was starting at 1 o'clock, going to 2. That's why nobody was there. So I'm going to change this thing to 2:30. Whoa, that was going to be a disaster. Okay. All right, let's go back. I think I'm already there. Can you hear me, guys?
Yes, we can.
Okay, good. Thank you. So this circle, control that circle, concentric. Very good. Excellent. So let me make this thing a little bit skinnier. Okay. On this end, I want a circle because I want to hold there. Exit. Pad it. That's too much. 0.5. Good. All right. Now we're going to insert the next part. So go all the way to the top. Save everything. Insert new part. Say no. Link to. Right click properties. Link to. Link to. Let's make it. Double click on it. On a convenient plane, on that plane, I will sketch. We'll project that circle now and do the rest of the link. So perhaps something like that. Now, if you make this thing too big or too small, you may have problems because these links, if it's too small, it may not reach the end of that path. And this is what happened to me earlier this morning when I was doing it for lab 51. I made it too small. It couldn't reach that path. It was a mess. Okay. We fixed it eventually, but it was spent a lot of time. That's why I couldn't do problem number 2. And I told them, you guys watch it from 52, lab 52. I don't know whether it's closed or not. We'll find out. If it's not closed, it's going to tell us. Okay, good. Now, I'm going to do a multipath because I want a pin on one side, a hole on the other side. So, 3 curves. Okay, let's start with the big one. Okay, this is the one at the place where we want to make a pin. So let's make this thing 1. Big pin. Okay, so this one is at the other end that I want to hold, so we leave it at 0. And this is for the entire boundary. I'll make it 0.5. Good. Okay, go all the way to the top. Save it. All right. Now, insert the vertical link. Insert new part. No. Vertical link. Properties. Vertical link. Okay, down here is the part name. Vertical link. Good, let's make it. Double click on it. On a convenient plane, on that plane, I will sketch. Project that circle. Exit. Pad it in both directions. Long enough so that it looks good and it kind of reached that thing. Okay, that's good. Good. All right, now remember, I need a point at the bottom of this because eventually I'm going to have a point curve joint. Eventually I'm going to have a point curve joint. So while I'm in vertical link, let me create a point at the center of the circle, this circle. Okay, good. That's pretty much it. Save everything. All right, let's go ahead and assemble. Now remember, this path could have been a separate part. I didn't. I make it belonging to the base. That's fine. So let's anchor something first of all. The base, which automatically include that path, we're going to anchor it. All right, now we're going to move things apart so that you have a good idea of what we're doing. So translate this way, and that this way, and there we are. And just to really screw it up, so let's also do a little of there. Okay, let's put it together. First, I'm going to put mount this link 1. So coincidence between this axis and that axis, and coincidence between. Since I don't want to fool around that much with those blue things, not the green arrows, I'm going to rotate. Update. There we are. Now I'm going to put that pin in that hole. So coincidence between this guy and that guy, and coincidence between this plane and that plane. I probably have to use the arrows here. Yep, that's what I thought. No problem. So you go to that last constraint, flip the arrows. Okay, that's better. Now I'm going to put this guy inside of that hole, coincidence between this axis and that axis, and update. Now notice that this can spin about its own. Right now it's going to turn into a cylindrical joint. Later on, if I use the magic wand, it's going to become cylindrical joint. And it has the ability to rotate, spin about its axis. And that's going to, we don't want that to happen. So what I'm going to do is I'm going to say, okay, whatever angle you have for a vertical plane of this, keep it the same when you compare it with the vertical plane of the link to. Here's what I mean. Look. Keep the angle the same. Angle of what? Angle of the vertical plane of this member, vertical link, and the vertical plane of this link 2. Keep the angle same, whatever it is. Right now it's 180 degrees. Fine. I'm okay. Keep it the same. All right? Now, the other thing is that later on, we want to do a point curve joint. For a point to be able to do a point curve joint, the point must be on the curve. Must be. And it's not. So let's put it on the curve. Coincidence between this point. Look, I can't pick it. Nothing. I can't pick this. So the thing is that you have to go to this part and make a point on this curve. So go to this part, which was the base. Make a point. The method to make it is on a curve. And I don't care what point. Any point will do. Look, it's the blue one. The blue one that I can move around. I can put numbers here and make it very precise. Right now it's there. It doesn't matter. I just want to point there. And go back to the assembly. Coincidence between this point and that point. Before I couldn't take it. There. Now, earlier today for the other group, I didn't. Eventually, I came and used it, but I started with coincident a vertical plane of the link, vertical link, and link 2 to be coincident. When you do that, you can do this this last operation. And when you think about it, you've got to sit down and find out why you cannot do it. Okay. I'm not worried about that. All I'm saying is that I tried to do coincidence, vertical plane. It didn't work because I could not put this thing on that. So I changed it to, for you guys, I'm changing it to angle constraint. This is why I asked the people in section 51 to watch the video, your video, okay? Because we didn't, we did it differently before. All right, good. So let's save everything. All right, so we go and digital markup, DMU kinematics, magic wand, new mechanism, auto create. So let's see if we can figure it out. Revolute here, revolute there. Prismatic here, because I did axis to axis and that trick of angle to angle or angle constraint. Right? Revolute, prismatic. Well, let's see. Revolute, prismatic. Whoa, there's something else that's created, spherical. The reason this spherical is created, and it's no good, you have to delete it, is because I made the bottom of the pin, of this vertical pin, coincident with a point on the curve. And I did not delete that. Because I did not delete it, it turned it into a spherical joint. All I wanted to do to make sure that the bottom of this vertical link is on that curve. So what I did, I created a point here, and I made a coincidence between the bottom of the link and this point, and then it took it there. But I should not leave that constraint because it turns into a spherical joint. But no problem. I delete it from here. It happens. Sometimes you do things that are not correct, but because of the constraint that you put, it's created and you have to go delete it. And now we're going to do a point curve joint between this curve and that. The reason I cannot pick it, because notice that there are 2 points sitting here. One was at the bottom of the link, the other one was on the curve. That's why it's trying to pick the curve now. It says you can't do it. If you already picked the curve, you can't take a point on the curve. So there's 2 ways to do it. Either hide this thing and get to the point that you want, or go to the vertical link. You remember, you created a point right there. You created a point at the bottom of this. So just go and pick it from the tree. Degree of freedom will be 1. You can make one of these angle driven or this one length driven. Point curve, length driven. The length of this thing, the length of this circle is roughly 21.7 inches, 21.8 inch. Okay. Now, obviously, mechanism can be simulated, and then you can go there. Oh, what? Oh yeah. Oh, hang in there. I made that. Oh, this was simulation with loss. That's not what I wanted. Simulation, what I want. Okay, so it goes like this. Put it at 0. Put it at 0. And the reason it's not set at 0 is because, remember, I created a point here. This point is not the 0 point of the curve. It just randomly selected them. So put it at 0 right there. And now you can go and do simulation. And it start at that position that I selected. See that? Insert, rewind, anything but 1, make it chase all the way around. That's what you want. Yeah, cartoon. Now we're going to put some physics into this. Okay. So let's say that the velocity of this point is 1 inch per second. I mean, this is ridiculous, meaningless, because these dimensions, I didn't even pay attention to what they were, but it doesn't matter. Let's say 1 inch per second. Okay, so we know what to do. We're going to go f of x, mechanism. Only the 2 things that are related to mechanism are going to show up. Add the formula, 1 inch divided by 1 second times time. Now time is here, but scroll down to get it. Right there. Constant speed. Okay. Now, I want to plot the acceleration of this point. The speed is constant. I want to plot the acceleration of this point as a function of time. Well, first of all, I want the acceleration of some point. I need the sensor. Reference product is the base. The point that I want is this point. Now, if you're not sure of this point, the bottom of the pin, say OK. Now we're going to do simulation with loss. Okay, if this is 22 inches, almost it was 22 point something inches, and this is going at 1 inch per second. So if I go, for example, 45 seconds, it's going to go. This is going to go around twice. Okay, so roughly 40. I don't know, 45 seconds. Okay, remember this thing was 22.5, something like that. And it's just going at 1 inch per second. So that means one round is going to take almost 25 seconds or 22 seconds. And then second round, another 22 seconds. So this is total duration. Activate sensor. What did I say? Acceleration. Not the X component, not the Y component, not the Z. Magnitude of the acceleration. Magnitude of the acceleration. It doesn't say magnitude, but it doesn't say X, Y, Z either. So that must be it. Now, move this thing out of the way. Play it. Once, twice, almost. Good. Graphics. So what I'm going to get is the acceleration of that point as a function of time. That looks like a constant. Yeah? That looks like a constant. Can you tell me, based on your dynamic stuff, is this right or not? I mean, do I have an idea how good this thing is? Where are you guys?
It is an acceleration graph, so it should be right, no? So,
But why is it constant?
the acceleration.
The question is, why is this thing a constant? I mean, I don't know why you're saying because it's acceleration. You said that it is right. I don't know on what basis you're saying. I'm not saying you're saying it the right thing or not, but what is your justification? And then I said, can you explain to me why is it constant? If you're saying it's right, you should be able to justify that.
Right.
Anybody else would like to pitch in? Let me ask you this. At the end of the day, we have a circle, don't we? That path is a circle, isn't it? That path is a circle. I agree. I draw it as a circle. Is it a circle?
And so we have linear acceleration here. Is that something to do with that? The graph we have is, it says linear acceleration there.
Well, linear acceleration means magnitude of the acceleration. Magnitude of the acceleration.
Okay.
That's what it means.
Okay.
Well, let's think about it for a second. You have a circle. It is true that it's on a slanted plane. I understand that, but it's a circle. And a point on it, and that point is the bottom of that pin, that vertical pin, is going around the circle at a constant speed of 1 inch per second. Do you agree? Yeah. That's what I said. I said, make it 1 inch per second. Isn't that r radius of the circle times omega? If something is going around the circle at angular velocity omega, the velocity of it is r times omega. R is the radius of the circle, omega is the angular velocity. So the angular velocity is constant, obviously. What is the tangential acceleration of this point? 0. The tangential acceleration of this point is 0 because it's going around the circle at a constant speed. What other acceleration it has? Normal component of the acceleration. Remember, r omega squared. R is constant, omega is constant. So this number is your r omega squared, constant. If I had made it an ellipse, that would not be constant, because the minute it gets close to that major axis, it wants to turn rapidly, not at a constant, so it's not a constant. But here it is. That's correct. This is why this is just a flat line. Here's some physics. Okay, are we good with this? Are there any questions about this? Always rewind. And remember, you have to do a screenshot of this. If this was on a test, we will ask you to do a screenshot of that plot, which I closed. Paste it in a Word document, name it in a meaningful way, and submit it as one of the items on your test or your homework, whatever it is. Okay, so let's move on. We have 60 minutes to do the other problem, and we will. Yeah. I don't want to. Okay, save that. What's the second problem? The second problem is an arm. What is this? Oh, wait. An arm which is mounted on that base and is turning at a constant speed. And there's a collar on it, and that collar is traveling along that arm at a constant velocity, constant speed. So we have an object that moves on a thing that is rotating. That leads to Coriolis acceleration that you did in your dynamics class. And you did the formulas and things like that. I'm not going to worry about it. I'm going to model this thing. Okay. So this is, if you look at the acceleration, if you look at the acceleration of the block with respect to the arm, it is 0. Block means collar. Okay. With respect to the arm is 0. But there is a normal component because this is rotating, and there is a Coriolis acceleration, which is the so we're going to model that. The only thing that matters here is really the size of, is 8 inches. Where is that? I have it here. 8 inches, and then the radius of this top piece is 0.5. So let's go ahead and do that. Start with the product file. Immediately save it. Let's switch to assembly design. Right there. File, save management, save as, desktop, new folder, 1111, lab 52, or did I call this thing, did I call the other one? No, Coriolis, yeah. That's where you guys came in and said the microphone is not working. I did all of this for no reason. Coriolis. Okay, let's do the base. Insert, new part in there, right click, properties, base. And this is the instance name and the base. All right, make it. All it is a circle. Let's stand where this arm is sitting on. So there we are. Exit. Pad it. 0.5. Excellent. Arm. Insert. New part. The arm, rotating arm, basically. That's what it is. Properties. Arm. And arm. Make it. Double click on it. On a convenient plane, on that plane, I will sketch another circle. Now the radius of the circle is important because 0.5, I mean, this guy is on that arm, so this radius is important. So radius is 0.5. That, oh, I'm sorry, what's the diameter here? Diameter, yeah, radius is 0.5, that's correct. Yeah, the diameter is 1. Okay, good. Exit. Pad it. Say okay. I'm not done though. On this vertical plane, I will draw that little thingy sticking out by 8 inches from that point. Exit. Let me give this some dimension here. 0.25. How about that? It doesn't matter, but I like it. Okay. Exit. Pad it by 8.5 inches. 8.5. There we are. So that color starts there. Okay. Okay, so what have we got here? Anything else? Nope, this is it. Save it. Now we have to do the color. Insert, new part, color. 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 Let's make it. So on a convenient plane, on that vertical plane, I will sketch. Okay, let me project this circle. I know what it is, but the circle already is 0.5, but there we are for lazy people. Okay, so, and then I'll do another one because it's supposed to be a hollow pipe type of thing. There we are. Exit. And pad it. Now, the size of it is not important. However, what I would like to do is I'll make it 1. And in fact, I don't want it to start from here. I want to start from there. So I suspect I can do that by saying this being, oh, no, the other way around. You know what? I'll do it a different way. Never mind. We do it a different way. So that's good. No problem. Okay. So let's I need to, at the end of the day, I want to plot the acceleration of the tip. I mean, basically the center of the circle. So let me create, while I'm in the color, let me create a point, center of that circle, and I'm going to use that to get my acceleration plot. Okay, now we go there, save everything. Anchor the base. We have a revolute joint between this and this. So axis of that and axis of this, and coincidence between. I want to show you something about the offset, but that's okay. I'm not going to do that. So let me do this plane, and I want to take the bottom plane of that middle thingy. You probably know this trick, by the way. Instead of rotating and moving this, you put the cursor on this part and use the upward arrow, so it marches through all the stuff that is there, and it's not the one. Ah, this is the one that I want. So that's good. So this is going to be a revolute joint. Now I want a prismatic joint here, and for a prismatic joint, I want the axis of this, axis of the color, and the axis of this to be coincident, and the vertical plane is the same trick that we used before. We can keep either the plane of these things coincident or angle constant. So let me do that. Coincidence between this axis and that axis, and you can keep the angle constant. We can also use coincidence of the vertical plane. So vertical plane of the arm, doesn't matter which one, and the vertical plane of the collar. This, what is fully redundant? Okay, why is that? Cancel. Okay, so what constraints do I have here that makes that thing fully redundant? Let's see now, axis and axis. Okay, this is the revolute, and this one, axis and axis. Now I try to do angle. Let's try it. Let me see. Let's try it one more time. So the vertical plane, what is this? Oh yeah, XZ plane. XZ plane and the XZ plane of the collar. No, the arm. I think I selected YZ plane. That's what it says. That's no good. I mean, think about it. That's no good. The other one was no good. Okay, now I also want this thing to start 0.5 inches away. So the best way of doing this thing is put a constraint here. See that? Offset constraint between the YZ plane of the collar and the YZ plane of the arm. And the value I want it to be 0.5 so that it pushes it. Oh. the other way. Minus 0.5. That looks good, see? Starts at the right location that I want. Okay, so save everything. All right, we're going to go to digital markup. Magic wand. There's going to be a revolute here, a prismatic there. Okay, new mechanism, auto create, and obviously the degree of freedom is going to be 2. Oh, wait a minute. Wait a minute. Oh, rigid. Okay, no problem. Delete this. So don't worry about it. We're going to do the prismatic ourselves. Prismatic. Let's think about it. The axis of the collar and the axis of the arm, and I'm going to cheat to the vertical plane of the collar. Vertical plane of the collar, XZ, and the vertical plane of the arm. That's going to become a prismatic. Yep. Now, degree of freedom is 2. That doesn't surprise you because rotation of the arm has nothing to do with the position of this. So what we can do, let me show you something. So angle driven 0 to 360. Prismatic length driven from 0 to, I don't know, from 0 to 10.5 in the other direction. Flip, okay. 0 to, I don't know, 8.5 or 8 inches. So then it says mechanism can be simulated, but look at what happens. This is fine. There's nothing wrong with it. This is a 2 degree of freedom system, regardless of how you slice it. These are independent of each other. It's just like you driving a car. The steering wheel and the gas pedal, they're under your control, but there are 2 degrees of freedom, independent degrees of freedom. Okay? So now what we're saying, we're going to say, okay, we're going to tie these things to time by saying that this has a speed of 1 inch per second, and this rotation has a speed of 1 cycle per second or 60 RPM. So this is fine. There's nothing wrong with it. So what we're going to do now is going to say, okay, we're going to do f of x, mechanism. These are the 2 things that are independently of each other can be specified. So the angle, the formula, 360 degrees per second. So if it's 60 degrees per second, 1s times time. You tie these things to time. This is not a single degree of freedom system. And this one is the speed, the formula, the speed mean speed of the collar, 1 inch per 1 second times time. Say okay. Let's make this thing go around, I don't know, maybe 2 seconds. It goes around twice. So let's go do a simulation with law. First of all, let's make sure this thing works. Simulation with laws. We're going to set the sensors in just a second. Over 2 seconds. Let's watch it and see whether it's what we want. Okay, let's play it. Okay, well, maybe we want to make this thing go faster. Okay, I mean, no, not really. That's okay. We're going to change the time more. Let's make it, I don't know, I guess 8 will go, this one will reach the end. So, okay, so let's make it go faster visually, okay? Oh, just too fast. This is not physics. This is, why is this thing go? Okay, yeah, good. Rewind, okay. Now we go and set our sensors. So reference product is the base. And the point is this point. Activate the sensor. Activate the sensor. What do you want? Magnitude of the acceleration. There we are. Magnitude of the acceleration. This linear acceleration. See that? Play it. Graph it. Yeah. That is also constant. Let me remind you why. Let me remind you why. If you go back to your dynamics courses or dynamics course on Coriolis acceleration, the Coriolis acceleration has several components. There's a tangential one, there is a radial one, and there is the Coriolis, which is the product of velocity and angular velocity. So for this particular problem, they're all constant. So the magnitude will also be constant. Okay. Now, if you want a different component of it, so let's go ahead and get it. So let me rewind here. Not the magnitude, but let's try something else. Now, these are also going to be constant. These are also going to be any. Of course, z is going to be 0, but these are also going to be constant. Linear acceleration. So rewind. Play. I don't know whether I cleared the history or not, but I don't think I did. Rewind. Clear the history. Clear the history. Play. I think I didn't. I also asked for the magnitude, so there's going to be 2 graphs here probably. Did I not ask for something? Okay, let's rewind it. Try it again. History clear. What am I asking for? I'm asking for the I don't know y component. Acceleration y component. Okay, and this is yes, and this one, oh, I think I asked for x. Okay, fine. Y component is the magnitude. Did I ask for the magnitude also? No, I did not. So it's single curve. Okay, so let's play it. I should get 1 graph. Why am I not getting it? Did I? Something is not right. Is it? Maybe it's down there. Maybe there. No. Oh, it was down there. Okay. It was down there. So y component. Now this is giving you 0. That does not make sense. Y component. Oh, angular acceleration. Of course it's 0. Damn. Okay, so I don't want angular acceleration. Angular acceleration because it is going at a constant speed. Where was that guy? Not this. Linear. I want linear one. Linear one. Linear acceleration. For example, y or x, it doesn't matter. Rewind. Clear the history. Play. Why is my graphs all hiding down there? Oh, there. Okay. This agrees with the physics. To verify that, go and open your Hippler's book on dynamics and check it out. There is a problem like that, by the way. Somebody walking at a constant speed on a merry-go-round as it turns. The merry-go-round is that arm. That somebody is the collar. Okay? All right, folks, we went 5 minutes overboard. Now you remember on the test, if we ask for something, you screen capture, put it in paste it in the Word document, and submit it. Now, their other homework assignment has been posted. I'm not giving you any dimension, just like the robotic arm problem. I say use your own dimension, make this thing work. And on the final exam, I can guarantee you there will be a problem where we leave it to you just to look at the picture and create the mechanism. And then we also give you stuff like this, where you have to generate plot, and we have to give you dimensions, obviously, and the speeds and everything, and whatever else. Are there any questions?